The following program is brought to you by Caltech.
I want to tell you a little bit today about Murray's work over many years. I want to establish one thing right at the start, that his interest in understanding quantum mechanics is not the late time decline of a great physicist. Murray has always been like this. Here, for example, on the right, when I came to Caltech as a beginning graduate student in 1960, Murray was teaching introductory quantum mechanics. It was a remarkable course in many ways. I was so impressed by his lectures that I took my class notes home every night and transcribed them with appropriate comments, trying to understand what they meant. And here is a copy of one of those pieces of notes. It's Murray discussing the theory of measurement in quantum mechanics, which was not exactly a usual thing in those days. And you can see down here a little picture, right? He's discussing, I think, a measurement of spin. There's the apparatus, some dial. And there's actually a little bit of premonition of the notion of histories. There are different histories of things that happen in the measurement process. And he says lots of interesting things on this page. But most importantly, he says this quantum mechanics says that both branches really exist. Both channels, as he calls them, both parts of the density matrix are there, and there's no reason for neglecting one channel over the other. So this was 1960, and he was already interested in this subject. Go forward a little bit, and you can learn from Murray's talk, for example, on the Web of Stories, that he, Felix Villars, and Feynman, continuing to seek to understand quantum mechanics, essentially recovered what's now known as the Everett interpretation or the Everett formulation of quantum mechanics, although I think nothing was ever published as far as I know. Now, why today should we continue to be interested in this question many years after the development of quantum mechanics itself? The reason is cosmology. We live in a quantum mechanical universe, presumably. It would be more interesting if we did not live in a quantum mechanical universe, but we have no evidence today that everything that we see can't be explained by quantum mechanical theories. All our fundamental theories are couched in those terms. And there is no reason to believe that quantum mechanics has all the experiments to set a limit on the scale to which it applies have so far failed to yield anything. So if the universe is a quantum mechanical system, then it has a quantum mechanical state. And therefore, it's a part of theory to ask what it is. If you don't have a theory of the quantum state, so we need a theory of the quantum state, what it is. That's the objective of a little subject that's come to be called quantum cosmology. Okay. If you don't have any theory of the state, then in principle you don't have any predictions. Every prediction depends on the quantum state, if only very weakly, because in quantum mechanics, probabilities of what you might measure or observe involve both the Hamiltonian and they also involve the state. Here's a projection operator on some quantity you might be interested in measuring. You apply it to the state, square it, you get the probability that that happens. The evolution of the state in this Heisenberg picture, which I'm writing down here, is given by the Hamiltonian age. So you need both a theory of the dynamics and you need a theory of the state. Therefore, contemporary final theories, which is the objective of much of physics, really consist of two parts. They consist of the theory of the dynamics, For example, superstring theory, which of course Murray has also advocated, and a theory of the quantum state of the universe, like the no-boundary quantum state. Every prediction in physics depends on both, but it's an interesting question of which regularities that we see in the universe depend more on one, the theory of the dynamics, or a theory of the state, and that's largely going to be the subject of my talk. So we ask the question, what regularities of the universe come mostly from the Hamiltonian, if you like, or the theory of dynamics, and what come from the quantum state? In addition, I won't address, because I don't know the answer, why the theory is formulated in this way. That is, why there is a division between a theory of the state and a theory of the dynamics. I believe that there is actually an unfinished task for physics of unification. But here is a short list of some features of the universe and whether they're more attributable to the theory of the dynamics, the Hamiltonian, or more to the state. So on the state side, we have certainly classical dynamics. The orbits of the planets don't depend on the initial state very much. Laboratory experiments, for example, those done at CERN, all of them also don't depend very much on the initial quantum state, at least in its level of details. But on the other side, there are lots of things on larger scales that do depend very much on the quantum state. Indeed, the fact that we've had a theory of the Hamiltonian for a long time and a theory of the state only for a short time is due to the evolution of our understanding. The Hamiltonian is local, it can be analyzed by experiment, and the state, however, describes regularities that exist in space, and it's only recently, with the development of large-scale observation in cosmology, that we've had a lot of information about what goes on in space. So the first item you seek to explain is classical space-time. In a theory of quantum gravity, there is no reason particularly to have classical anything if it's a quantum mechanical theory, any more than it is for any other system, right? To have classical behavior if it has a given quantum state. So that has to be traced to the state. That space-time, or those ensembles of possible space-times, have properties. For example, early homogeneity and isotropy, followed by the growth of fluctuations under the action of gravitational attraction and the expansion of the universe to give the large-scale structure which we see today. That, what those fluctuations are, once again, is largely a property of the fluctuations, as I've just said, start in their ground state. That's a statement about the state. Arrows of time, right, which the universe exhibits a number of them, a thermodynamic arrow, for example, the psychological arrow, and I'll come back to this in a little bit. Those are, in general, not the properties of time-neutral dynamical laws like we believe exist in the Hamiltonian, but follow from the state. The fact that we have isolated systems in the universe is not a general property of all quantum mechanical systems, but a particular property of ours. And the fact that there's the separation of the Planck scale from the other scales in the universe, that we don't have to deal with quantum gravity until very late. Other particular properties, the topology of the large-scale space-time is a property of this state. Is it a sphere, a torus? The number of large and small dimensions, the number of time dimensions, why there's a separation between one time dimension and many space dimensions, and the coupling constants of effective theories to the extent that they're not supplied by the Hamiltonian but are variable in a landscape of different possibilities for these coupling constants, as, for example, in contemporary theories of the cosmological constant. So we need to apply quantum mechanics to cosmology. But textbook quantum mechanics, as you read about it in the textbooks, has to be generalized for applications to the universe. It's not sufficient. The usual theory that you read about predicted only the outcomes of measurements, and it assumed a separate classical world, or what's the same thing, a classically behaving observer. But measurements and observers can't be fundamental notions in a theory that seeks to describe the early universe when neither existed. And in a fundamental quantum theory, there's no reason for there to be any variables which behave classically in all circumstances. So Murray, helped by me, has come up with the idea of decoherent histories quantum mechanics, which is general enough for cosmology. I'm just going to take a few slides to describe that to you very quickly, right? I'm going to describe it in a kind of model universe in which everything is living in a box, perhaps 20,000 megaparsecs on a side. It may be expanding, but everything is in there. Planets, stars, measured, what's doing the measuring and so forth. The important thing is that there is no observer on the outside that's looking at the box. So you have to formulate quantum mechanics without the notion of measurement, without the notion of observers, and even without the idea of classicality. The theoretical inputs of this formulation are what I've just discussed. We presume the final theory has both a theory of the dynamics, the Hamiltonian, and a theory of the state. And from that, we need to calculate probabilities about what goes on. Now, the most general objective of any quantum theory is the prediction of the probabilities for members of sets of coarse-grained alternative histories of the closed system. For example, suppose we're talking about the orbit of the Earth around the sun. Then we would like to discuss an orbit, means discussing positions at a series of times at least, right? And seeing whether they line up, if we're interested in classical prediction, in a way that is consistent with classical deterministic laws. In quantum mechanics, the Earth could take any orbit as it goes around the sun, and there's a probability for it to take any orbit. The reason we say it behaves classically is because the probability that it is high that it moves on an orbit determined by Newton's classical laws. So we're interested in probabilities of histories, and I said coarse-grained histories. You know, when we're discussing the Earth, we're discussing, say, just the motion of the center of mass of the Earth and not the other 10 to the 80th particles in the visible horizon. We discuss these only at a few times and not every time. And we discuss them only to a certain accuracy, because if we discuss them precisely, the Earth would not move in a classical orbit. So in a general formulation of quantum mechanics, we want to assign probabilities to histories. But there's an obstacle to assigning probabilities to histories in quantum mechanics, and that obstacle is quantum interference. For example, here's the famous two-slit experiment where we have an electron gun. An electron moves through one of two possible slits to detection on the screen. If we have many electrons, we get the characteristic interference pattern. It's not possible to assign probabilities from the theory, of the Hamiltonian and the state, to whether the electron went through the upper slit and the lower slit. That's because in quantum mechanics, probabilities are squares of amplitudes. And the square of the amplitude to go through the upper slit and arrive at y plus the amplitude to go through the lower slit and arrive at y is not equal to the sum of the squares. And therefore, the probability to arrive at y is not the sum of the probability to go through the upper slit to arrive at y and the probability to go through the lower slit. It's not that we don't know which what it did, in which case the probability would be 50-50. It's inconsistent to discuss probabilities at all. So interference is an obstacle to formulating probabilities for histories. And some rule is needed within quantum mechanics to say what sets of histories can be assigned probabilities and what cannot. In ordinary textbook quantum mechanics, the rule is simple. It's you can assign probabilities only to sets of histories that have been measured. If you measured which slit the electron went through, the interference pattern is destroyed, some rule is obeyed, and everything is fine. If you didn't measure which slit it went through, who cares anyway? But that's exactly the kind of rule we can't have in cosmology, because it's focused on measurement. It assumes that a split of the system into measured and not measured, we need a more general rule. And the rule in decoherent histories is very simple. You can assign probabilities to sets of histories that decohere, meaning the interference between the alternatives vanishes in fact between the members of the set as a consequence of the inputs to the theory, the Hamiltonian and the state. So decoherence supplies consistent probabilities. So that's it. That's decoherent histories, quantum mechanics in a nutshell. I should hasten to add that decoherence is widespread in the universe. In the classic example of Yos and Say, if you have a dust grain, this is one dust grain in a superposition of two positions, say deep in interstellar space, the superposition is decohered. The relative phase between the two positions is dissipated in the order of about a nanosecond just from the 10 to the 11th microwave background photons that strike it every second. They carry away the phases, affect decoherence, and you can talk about probabilities for whether the dust grain is in one position or another. So decoherence is a more general, more observer-independent rule for assigning probabilities in measurement. And that means we can assign probabilities to the things we always wanted to assign probabilities to the position of the moon when nobody is looking at it, and density fluctuations in the early universe when there were no observers or anything else around, and all sorts of other possibilities that are important for cosmology. Now, I mentioned that the usual formulations of quantum mechanics assume there was a kind of separate classical realm. And certainly in our universe, there's a whole domain of applicability of classical laws. We could call that the quasi-classical realm. It's a feature of our universe, not necessarily the feature of every universe. What I mean by it is the wide range of time, place, and scale on which laws of physics actually hold to an excellent approximation. We believe that's roughly from the Planck era forward to the infinite future. Place, everywhere in the visible universe. If we were to journey to a distant galaxy, we don't believe we have to equip ourselves with special equipment, right? Classical physics is going to hold there as well as here. And on a scale, all the way from the macroscopic to the cosmological scales. It's only when you do very delicate experiments that you actually see deviations. In a theory that doesn't posit the existence of the classical realm, as Copenhagen quantum mechanics does, you have to seek to explain it. So we can ask the question, what is the origin of this classical realm in a quantum universe characterized fundamentally not by the determinacy of classical physics, but by indeterminacy and distributed probabilities? And we're not interested in just classical behavior of a few systems of our choosing, like the moon or the Earth. We're interested in classical behavior over the whole world of the visible universe and over most of its history. So once again, the formulation of quantum mechanics that doesn't posit the quasi-classical realm has to explain it. And that's particularly important in cosmology because the observed features of the universe are the features of its classical behavior. We learn about the cosmological constant. We measure it by observing how it classically evolves. We learn about the growth of density fluctuations by seeing them as a classical feature of the CMB. So we have to do this both for cosmology and also just to understand quantum mechanics. But to do that, we need a theory of the state, right? Because it just won't be true for every state. So we need a wave function of the universe. I'm talking about wave functions in the universe. I want to stress a few things right away. A state of the universe is not an initial condition. Well, I've used that term myself many times. We're talking about quantum gravity here, the emergence of space-time, and there is no space-time in which for something to be early or late. So rather, a state predicts probabilities for possible alternative four-dimensional histories that may be correlated in time by Einstein's law, and thus classical. What went on then, what goes on now, and what will go on in the future. So we take a fully four-dimensional point of view of quantum mechanics, that the state predicts probabilities for these histories, and seek to do that to make those predictions using the decoherent history quantum mechanics that I've just described. I now want to talk about one particular notion of the state, which is the no-boundary wave function. Our observations of the universe suggest that early on it was simpler than it is now, more homogeneous, more isotropic, more nearly in thermal equilibrium. That suggests that is consistent with the idea that the universe was very symmetric early on, which is characteristic, typically in ordinary quantum mechanics, of ground states of the system. So I'd like to explore the idea, the no-boundary wave function is a manifestation of the idea that the universe started out in what's the cosmological analog of the ground state. Now, you're used to thinking of a ground state as the lowest eigenstate of some Hamiltonian, but if we're going to deal with closed cosmologies, which is all I'm going to talk about here, there isn't any lowest eigenstate of the Hamiltonian, because due to reparameterization invariance of the time, the Hamiltonian vanishes in a closed universe of general relativity. So if you want to talk about the ground state, you've got to define it in some different way than than an eigenstate of a Hamiltonian. But already in ordinary quantum mechanics, there is such a way. You can just define the ground state in terms of a certain Euclidean sum over histories. We can't do that, but we can define it as the Euclidean sum over four geometries of a particular kind that they have, and I'm not going to try and do this in any detail. They have one boundary. Here's a sort of famous shuttlecock model of it, where you have one boundary, 2 dimensions less than the 4 we have, and much less than 10 also. One boundary which has the argument for the state and no other boundary. Sum them over Euclidean geometries of that kind, construct the path integral in the right way, and you get the no-boundary wave function. So the question is now, how well does it deal with this list of theories, classical spacetime, early homogeneity and isotropy, and so forth. I think I can't hope to go through all of these, right? So I'm just going to pick 2 to describe how it works. First of all, we have to get the predictions of the possible classical histories. So as I think I've said before, classical history is one whose alternatives are correlated in time by classical deterministic laws with high quantum mechanical probabilities. If the probabilities are high for those correlations, then we say that the system behaves classically. The no-boundary wave function predicts an ensemble of possible classical histories for the universe in which these features can be assigned probability. That is, it predicts probabilities for histories that inflate and histories that don't inflate. The probability is high, as it is when appropriately calculated, then you predict that the universe inflate. If it predicts arrows of time, that is, for example, the thermodynamic arrow, then you explain the thermodynamic arrow. Does it predict the CMB as the evolution through reheating of quantum fluctuations that have become classical in the early universe? Does it predict isolated systems? What topology does it pick, and so forth? But I'm only going to pick 2 of these. One for which the theory is a success, and the other to balance it out. One in which we don't have as yet a success, but might be of interest to Murray. So I've already said all this. We live in one of these histories. Its probability is proportional to the probability for our observations. So let me take the arrows of time as an example. Our universe exhibits a number of different arrows of time. There is the fluctuation arrow, which is the growth of density fluctuations from initially in their ground state, certainly as small. That picture is successful in explaining the spectrum that we see in the CMB. There's the thermodynamic arrow, the fact that presently isolated systems are all evolving towards equilibrium, roughly in the same direction of time. That was explained by Boltzmann 100 years ago as arising from the fact that the progenitors of those isolated systems were all far out of equilibrium at one early time. But you have to be able to explain that also from the state, the growth of entropy. The radiation arrow, the fact that electromagnetic radiation is retarded as far as we can see. And the psychological arrow, at least one of the psychological arrows of time, the fact that we remember the past, experience the present, and predict the future. With time-neutral dynamical laws that don't single out any such directions in time, these can be explained, right, by a theory of the state that provides, in effect, boundary conditions for that, for the variables that change. These arrows are not all really independent. For example, basically, the fluctuation arrow determines all of them. The thermodynamic arrow arises from the growth of fluctuations and then their collapse and dissipation. The radiation arrow means can be discussed just because seen as arising from the fact that in wavelengths outside of the microwave background radiation, there wasn't much radiation, and the fluctuations were very small in the early universe. And the psychological arrow can also, to a certain extent, explained from these other arrows. Okay, so I'm going to take a little simple example here of how the state explains the origin of these arrows, and one which is non-trivial, right? Because as we'll see, we're going to get two arrows. I'm going to take a case, the no-boundary wave function. I mentioned that it predicts an ensemble of classical geometries for the universe. It predicts geometries that are initially singular, they recollapse, but it also predicts bouncing universes. There's a cosmological constant in there, which I haven't described in any detail. It looks like this, where the universe is initially large, if you like, whatever initial means, and then collapses to a minimum radius and then re-expands. It's just like de Sitter space. It's a very simple example. So now we want to look at the fluctuations around this. And the question about arrows of time, at least as far as the fluctuation arrow, is where are the fluctuations small? Away from those directions? Is it on one end and they grow all the way through? Or is it in the middle? Or is it on the other end, if that makes any difference? That sum over Euclidean histories that I described for you can be evaluated, it's just an integral, it can be evaluated by steepest descents. The saddle points, the geometries that occur, are called fuzzy instantons for no good reason. And they have the property to exhibit fluctuations up here, but the fluctuations vanish down here at the south pole of the instanton. That vanishing of the fluctuations means that the fluctuations are small at only one of the places in the universe where the universe is small. Well, in the bouncing universe, the universe is small down here, and that turns out to be where the fluctuations are small. Therefore, the fluctuations grow away from the bounce on either side, right? And times arrows actually points in opposite directions on opposite sides to the bounce. That's going to make it difficult, if we live in such a situation, to get any information out from the other side of the bounce, because the people living on this side have as much chance of sending us information about what's going on as we have sending information back into our past, telling people to vote differently in some election. It's not going to happen because of the thermodynamic relativity. I might add, Sean Carroll and Jennifer Chen have similar ideas, right? Although not expressed in this wave function of the universe formulation. I picked them out just as I check. Well, we should support Caltech. Not to mention Sean. Okay. Okay, the second idea I want to try is the evolution of complexity in the universe. Just on some intuitive level, the early universe is simple. It's homogeneous, isotropic. These fluctuations, after all, in temperature, which are what are shown in this picture, are really only 1 part in 10,000. The actual picture to your eye would look like this, completely uniform. And of course, there's this little thing for the galaxy I haven't turned down. But as we evolve, the complexity in the universe intuitively increases. The universe develops various inhomogeneous structures, stars, galaxies, planets, biota, universities, conferences with different numbers of people that sat in different places, all things that would take a very long time to describe. In other words, the algorithmic information content of the description of the system has gone up from something that's very easy to describe, it's the same everywhere, to something that is complex to describe. The late universe is also going to be simple, because if we wait long enough, the proton will decay, the stars will die out, the black holes will evaporate, there will be, temperature will be almost close to absolute zero, it'll be dark, black, and simple. So complexity doesn't always increase. It starts simple, it gets complex, and it gets simple again. So how is that connected to the simplicity of the fundamental laws? The no-boundary wave function, and I haven't described it to you in any detail, is simple. It only, I hope I counted correctly, takes 45 LaTeX keystrokes to write it down, and only a few physics textbooks to explain what the formula means. Is that connected in any way to this evolution of simplicity of the universe? I don't know. I'm hoping Murray will help explain this. Well, I had a lot of other things on the list. I don't propose to use your time trying to explain them, but I have a kind of scorecard for the no boundary wave function in decoherent histories, what that succeeded. I'm just going to state, you can ask in the question period if you like, right, what to take. So classical Lorentzian spacetime, yes, it does explain that within simple theory of quantum gravity. Early homogeneity and anisotropy, well, the construction was essentially Euclidean. So it's only natural that the fluctuations start in their ground state. And it predicts inflation with the appropriate probabilities. Fluctuations start in their ground state, yes. Hours of time, yes. It predicts early simplicity, the evolvement of complexity. Isolated systems, well, these fluctuations grow, collapse, right? And then thanks to nuclear physics, right, they, which means the nuclear forces saturate, they don't keep on collapsing, they stop and they make stars and planets and so forth. So yes, it explains that. And the separation of scale, of course, is explained by the expansion of the universe. The temperature goes down to 3 degrees. That's very far from the Planck temperature. We don't have to worry about this. Once again, because of nuclear physics, we don't have to worry about very high energies in describing the everyday things that we see. The topology of the space-time, well, there's no evidence for complicated topology from the CMB. There are hints for that we can explain the topology of space-time. Let me not go into one. Number small, large dimensions, yes, right? Might be able to assume the 4 and predict that the others are small. Coupling constants of effective theories, well, there's some information about that. For example, there are well-known anthropic arguments for the value of the cosmological constant. If we live in a landscape in which the cosmological constant varies, it may be that most regions of the universe have cosmological constants 10 to the 120 the size of ours, but we don't live there. Galaxies wouldn't form, as explained by Weinberg, Barrow, Tipler, so forth a long time ago. Once again, that's calculating the probabilities for we exist in this large universe. So some coupling constants can be explained that way. Is it connected to the fundamental theory at all? Well, there's some recent evidence for that, and that we can give a formulation of the no boundary condition, at least at the semi-classical level, in terms of dual field theories with appropriately defined sources. Recent progress. But on that note, I think I'll stop. It just remains for me to thank Murray for allowing me to his student to help in this great problem. I think you can see here a typical interaction mode in which I'm explaining something to Murray, and he's looking very skeptical. That's possible. Thank you very much.